Okay, so remember this was the lower sum that we had calculated. Now in this case the upper sum is actually easier to calculate because not because it's an upper sum, because it depends on the function, but because this particular function, the upper sum corresponds with the right endpoint of each subinterval. So that would, and it's easier to do these calculations with the right endpoint because you only have to deal with x sub I rather than x of I minus 1. So I'll show you what I'm talking about here. The width of the rectangles are still delta x equals 2 minus 0 over n, 2 over n. But the x value where you get the maximum in the ith rectangle is actually going to be 0 plus I times delta x. In other words, it's I delta x units to the right of 0. And these are 0 because we're starting at 0. If we were starting at 1, if we were going from 1 to another number, this would be 1 plus I delta x, which actually throws a new wrinkle in there. Okay, so 0 plus I delta x. Now since delta x is 2 over n, I times 2 over n is 2I over n. So to get our upper sum for the area of the larger rectangles, we're going to sum from 1 to n the width times the height, and the width of course is 2 over n, and the height is f of 2I over n, because that will be the right endpoint. The right endpoint of each rectangle will actually be at 2I over n, and then we're going to sum that from 1 to n. Now we can factor 2 over n out, and we get the sum of f of 2I over n, and remember this is just the function x squared. So if we take 2I over n and square it, we get 4I squared over n squared. So we have 2n times that sum. Well, now I can factor the 4 out of the sum and multiply it by the 2 over n, so I get 8 over n. And then I can take the n squared and pull it out in the denominator and multiply it by n, and I get n cubed on the bottom. So ultimately I get 8 over n cubed times the sum of I squared. Now the sum of I squared that's pretty simple. The sum of I squared would be n, as I goes from 1 to n, would be n times n plus 1 times 2n plus 1, all divided by 6. And now if you multiply that out, well, before we multiply it out, let's factor this n out. If you factor this n out, you get 8n over n cubed, and that's going to give you 8 over n squared. Then you have n plus 1 times 2n plus 1 all over 6, which is 2n squared plus 3n plus 1 all over 6. And now I'm going to multiply the 8 through, and I get 16n squared plus 24n plus 8. And then if I multiply the n squared through, I get 6n squared on the bottom. And then if I break this up into the 3 terms, 16n squared over 6n squared reduces to 8/3. 24n over 6n squared is 4 over n. And then 8 over 6n squared is 4 over 3n squared. So the sum of the upper rectangles, or the upper sum, is 8/3 plus 4 over n plus 4 over 3n squared. Notice up here, the only difference is the middle term was minus up here. So obviously this sum is smaller than this sum. Okay, now here's what's interesting here. If you actually take each of these sums, and remember what I told you earlier, if you let the number of rectangles go to infinity, that would basically be letting n go to infinity. As you let n go to infinity, then the area estimation actually approaches the actual area. So for the lower sum, if we let n go to infinity, remember 4 over n and 4 over 3n squared would go to 0. So those terms would disappear, and we would just have the limit of 8/3 as n goes to infinity, which is just 8/3. But notice on the upper sum, the same thing's going to happen. The 4 over n and the 4 over 3n squared as n goes to infinity goes to 0. And so you have 8/3 again, so you get 8/3 plus 0. So actually, since the lower sum is 8/3 and the upper sum is 8/3, and remember we trapped the solution between the upper sum and the lower sum, well, there's no place for the solution to hide now, so the actual area must be 8/3. And so this leads us to this next theorem, and this theorem says for the limits of the upper and lower sums, let f be a continuous and non-negative on the interval a to b. The limits of both the upper and lower sums as n approaches infinity exist and are equal. So if they exist and are equal, like we had in this case, where s of n is this, and smaller lowercase s of n is this, and uppercase s of n is this one, and then delta x is b minus a over n. So in other words, if the function is continuous and non-negative over the interval from a to b, then the limits of both the upper and lower sums as n approaches infinity do exist and must be equal. So this means we can just find the easier of the sums and find its limit to get the area. Actually, it turns out we can use any x value in the ith subinterval. So it doesn't have to be the left endpoint, right endpoint, or the minimum or the maximum. It turns out it works for any value in that subinterval. Now, let's extend this by talking about the definition of the area of a region in a plane. Now, let f be continuous and non-negative on the interval from a to b. The area of the region bounded by the graph of f, the x-axis, the vertical lines x equal a and x equal b, is area equals the limit of the sum as I equals 1 to n, f of c sub I delta x, where c sub I is any number between xi minus 1 and xi. So in other words, any number between within the ith subinterval. And then delta x, of course, is what it's always been, b minus a over n. Okay, now finding the area by the definition. So let's take a look at an example. Say we want to find the area bounded by the graph of y equal x cubed, the x-axis, and the lines x equals 0 to x equal 2. Well, delta x will be 2 minus 0 over n, which equals 2 over n. So we can say that c sub I, since we can use any point, let's use the one where we only multiply by I. I don't care if it's the left endpoint or the right endpoint. I'm going to use the one where we just have the I times delta x. So I'm going to let c sub I just simply be I delta x. And so I times 2 over n would be 2I over n. So now, based on this theorem, the area is the limit as n goes to infinity of this sum from 1 to n, f of 2I over n times 2 over n. And now since f of 2I over n, remember f of x is x cubed. Where is it? There it is. F of x is x cubed. So all I have to do is cube 2I over n, which is going to give me 8I cubed over n cubed times 2 over n. Well, if you multiply these two together, you get 16I cubed over n to the fourth. But I can factor the 16 over n to the fourth out of the sum. And so I have the limit as n goes to infinity, 16 over n to the fourth times the sum of I cubed. And then the sum of I cubed, remember we had a formula for that. The sum of I cubed as I goes from 1 to n is n squared plus n times n plus 1 quantity squared all over 4. And then if I can take this 4 and factor it out here and have 16 over n to the fourth times 4. So 16 goes divided by 4 is 4. And also, actually, if I bring this n to the fourth, I'm going to bring it back inside. So basically what I'm doing is trading places with the n to the fourth and 4, just because that's the way I want to do it. So the n to the fourth, if it goes back in here, then this n squared over n to the fourth just gives me n squared on the bottom. So if you're wondering what happened to n to the fourth, that's what happened to it. So now I have 4 here. And remember, I can factor the 4 outside of the limit. So let's just put it out there and get it out of the way. And then when you square this, you just get n squared plus 2n plus 1 all over n squared. Well, remember that the limit of a rational function, which is basically what this is, when the degree of the numerator is equal to the degree of the denominator is just the ratio of the lead coefficients. And guess what? The lead coefficients are 1 in the top and 1 in the bottom, so the limit is simply 1. And out here you have 4, so you have 4 times 1 over 1, which is simply 4. So that area is just 4 square units. Now, it gets a little more complicated if you have to find the area, say from 1 to 2 of a function, but let me just show you this for a minute. Delta x in this case would be 2 minus 1 over n, so it would be 1 over n. C sub I now would be 1 plus I delta x, because we're starting at 1 now, not 0. So that would be 1 plus I over n, since delta x is 1 over n. Okay, now, so the limit would be the sum of f of 1 plus I over n times 1 over n. And go ahead and evaluate the function at 1 plus I over n, and you get 5 times that expression squared, and then times 1 over n. Well, I went ahead and squared this expression, and I got this term, these 3 terms. And then what I did next was I went ahead and combined 5 minus 1, and that gave me 4. And then so I have 4 minus 2I over n minus I squared over n squared times 1 over n. Well, I went ahead and kept the n on the outside, but I let the sum sneak on the inside here. So I'm going to say the sum of 4, sum of this, minus the sum of this, minus the sum of this. Well, when I did that, I went ahead and factored the 2n out of this term outside of the sum, and then I factored the 1 over n squared outside of this term outside of the sum, and I still have the 1 over n out here that I'm just holding for a moment. And now I apply my formulas for sum of I, and I get n times n plus 1 over 2. The formula for sum of I squared is n times n plus 1 times 2n plus 1 all over 6. And let's not get lost in the algebra here. Let me just go ahead and say what you're going to do is you're going to simplify all of this, and it's going to simplify to this if you do the algebra. I'll let you do the algebra. And then if you multiply this by 1 over n, you're actually going to get 4n times 1 over n is 4. And then here you're going to get minus n plus 1 over n. And then here, if you multiply this together, it's just going to be a polynomial, 2n squared plus 3n plus 1 all over 6n squared. So now if we take a look and evaluate those limits, the limit of 4 is 4. The limit of n plus 1 over n as n goes to infinity is 1. And the limit of this polynomial is just, limit of this rational function is just 2 over 6. So that would be 1/3. So I'd be subtracting, since that's minus, I'm going to subtract 1/3. So basically I have 4 minus 1 minus 1/3, and that adds up to 8/3. Now you can find a region bounded by the y-axis as well, but I'm just going to show you how to set that up. Let's say you want to find the area bounded by the graph of x equal y squared, and that's a sideways parabola. The y-axis and the lines y equals 0 and y equal 1. Well, you just sort of reverse things. So you're going to have delta y is 1 minus 0 over 1, which is 1 over n. And c sub I is actually going to be 0 plus, it should say delta y there, I delta y. And that's going to just be I over n. And so then you still do the limit the same way. You just exchange your y for your x's for your y. And so you're going to get the limit as n goes to infinity of the sum from 1 to n of I over n squared, because that's x equal y squared, so you have to square the y value, and then times 1 over n. And then I'll leave you to work through these steps, and then notice I ultimately get this expression, which simplifies to this expression. And then when you take the limit of this as n goes to infinity, you get the ratio 2 over 6, which is 1/3. Now, as the note said before, you're probably going to hate me, or maybe hate your instructor, once you get to the fundamental theorem of calculus, because you're going to find out that to find these areas, you don't have to do near as much work as what I'm showing you here. But we have to get there first, and this is one of the steps in order to get there. So we'll talk more